Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.3.9. So, in the dihedral group of order 8, do coset chunks preserve composition? Meaning, can we chunk up D8, like take a subgroup of it and take its cosets, and that's going to create a merge, right? And does that merge preserve the operation? Composition is the operation. So does it preserve the group operation when we chunk it up, depending on, like what kind of cosets we use? So, well, if we try, so we have a subgroup of H, right? And actually the subgroup of H, it chunks it into two parts. It has this part, and then the other part that it actually has is S applied to all of these. Remember those two separate chunks of this group that we were looking at, like this chunk, and we were looking at this chunk. So those are two chunks. And actually, when we do that and we say, well, we take the subgroup, which of those chunks is actually a subgroup? The first one. And the other one was just a shift of it. We were doing S to all of it. If we take those two guys, that actually is actually when we quotient out and just look at those chunks, the operation of composition is actually preserved, meaning that the rotation group H that we were looking at is actually a normal subgroup. However, D8 has a subgroup that's not normal. Remember that D8, we're working with permutations, and it's not going to be commutative. So, for instance, we have the two left cosets of H right here, and we actually do have a nice a nice thing going on there. Now, okay, cosets partition a group. So, these are fiber chunks and they partition the group there. All right, and there's a little proof of that in general. So now so we have this subgroup H, we have this subgroup S, which is, now what does this notation mean? This just means the subgroup generated by that element, the smallest subgroup that contains this guy. So that's like the identity, and actually this is its own inverse. If you look at the group table, actually right here you have a little group table. So actually this has two elements. This one has four elements. The smallest group that has the one rotation, we have to keep the rotation going, like it's closed, so you kind of have to do it to itself again. So this is just notation for the subgroup that's generated by that, the smallest one that has that, smallest one that has that. In that contains that. It's kind of a minimal property, just like meets and joins are kind of have some minimality or maximality to the properties that define them. So we take a look at this right here. Here's our table. One thing to keep in mind with these operations, let's just kind of look at this for a minute. You see, if you do, so for instance, like if you do S of R, okay, let's see, S of R right there, or if you do R of S. Notice that if you switch the order of S and R of S, what happens here? This one is S of R, this one is S of R cubed. Kind of like 1 and 3 add together to make 4. So it's kind of always opposite. So S of R, but R of S is going to be S of, if you reverse the order again, you're going to put R cubed is actually the inverse of R. R cubed composed with R is R4, which is 1. Or the identity, because it's R to the 0 mod 4. So, but anyways, that's one little note when you're looking at that arithmetic. Okay, now here's a question. Okay, well, we already got that. Okay, so I already mentioned this. This is something I already mentioned here. This, we have a little group table on cosets of H, right? There's only two cosets. Those are the two chunks we were talking about. And the operation of composition is preserved. In fact, it looks like mod 2 arithmetic. Really, you can do mod 2 arithmetic there with the cosets. of H and D8. So you have an example of H being a normal subgroup. It's behaving normally, it preserves the operation. However, okay, this is a little description of what I was just talking about there with that arithmetic. However, in general, there is a subgroup. So the other one, the one generated by S with two elements, if you like this one right here, if you mod out by that, or you try to look at its cosets, so its shifts, its composition shifts, just on one side. You don't do it on both sides, just on one side at a time. And if you do that, you actually can't. It doesn't preserve the operation, and that's basically what all this argument is. If you run through this is exact. It just kind of says, well, let's assume it does, and then you find a contradiction. So assume that the bars behave nicely, where you can split the bars over the operation if you mod out by S, okay? And then in this process, you actually find a contradiction. And so therefore it tells you, doesn't work. So it's not a normal subgroup. Thanks for watching.